Hi and welcome to question 3 of the 2009 Math Methods paper, paper 2, section 2. Okay, so question 3 is our probability question. Many of you aren't going to like this. I happen to like this. Let's get through this. So part A, let's look at the question. Sorry. Here we go. So we've got tennis balls with diameters that are normally distributed. The mean is 67 millimeters and the standard deviation is 1 millimeter. Awesome. Okay. And then, they get fit into cans and stuff, and it'll fit if it's less than 68.5 millimeters. Great. So, first part A, says, what's the probability of having a random tennis ball fit into the can? So, in other words, you want to find the probability that x is smaller than 68.5, right? So before you do that, write down x is distributed normally, mean of 67, standard deviation is 1. Great. And you want to find the probability that x is smaller than 68.5, right? Okay, cool. You can plug that into the calculator and it'll probably give you the answer. Just to be safe, maybe smart to draw a little graph. So this is my little graph. It's normal distribution. The mean is at 67. You know that higher than 67 you get 68.5, like that. And you're after this whole region here. Okay. This little graph is good. It shows the examiners that you know exactly what you're doing. Also, it gives you a check on the answer. You know that the answer should be bigger than half, probably a lot bigger than half, given that you're 1.5 standard deviations out. So if you punch that into your calculator intelligently, you're going to come out with 0.993. Okay, rub this out. 0.9332. There. Answer out, like that. Get on to a better question. Part B is a better question. So they want a diameter. So now, looking at part B, you want to find the probability of a ball being between 65.6 and 68.4 millimeters. Okay. Well, x is distributed as above. So you'd go, okay, well this is the same distribution. And all you want is the probability of x. You want the probability that x is between 65.6 and 68.4. Again, turn to your calculator straight off, and you'll see that you get 0.8385. 2 of the easiest marks you will ever get. Good, isn't it? It's got to give you some confidence. Now, that's really good. Really good. Part C, though, comes a slightly tricky part. That first section was worth 4 marks. This next section, C part 1, is worth more than the 1 mark that's allocated to it. Because it says, now what's the probability that the diameter of the tennis ball which fits into a tin is between 65.6 and 68.4? So, do you see that part A talked about fitting into a tin? What's the probability of that? Part B talks about having balls between 65.6 and 68.4 millimeters. Part C says a combination of the two. What happens if you have a tennis ball that already fits into a tin? What is its probability of fitting into that range, 65.6 to 68.4? First thing to realize, this is a given question. Given. It says, what's the probability of fitting into that range given it already fits into a tin? Once you realize that, this thing is super easy. So the probability is basically equal to the probability of x being between 65.6 and 68.4, given that you know that x is smaller than 68.5. Okay, cool. Now, you know how to work that out, and you know that the intersection of these two events is just going to be x between 65.6 and 68.4, right? So that's basically the probability of x between 65.6 and 68.4 over the probability of x smaller than 68.5. You know both of those already. Be very careful though. Don't use just 4 decimal places. It'll be smart if you actually go back to your calculator and type these in again. You'll find that the answer is 0.8985. You may or may not arrive at that final answer if you just got our 2 answers prior and divided them by each other. Maybe you will, maybe you won't. Don't take the risk. Alright, see part 2. What's it say? See part 2 says, okay, now you get a tin of 4 balls selected at random. What is the probability correct to 4 decimal places that at least one of these balls has diameter outside the range? Okay, what is going on here? What kind of distribution are we looking for? The answer is binomial, right? Every ball has the same chance of being outside the range, and you have 4 of them. Great. So, look at the distribution that you've been given. So, you know here that x is distributed binomially. Whoa, wrong color. This is happening a lot today. X distributed binomially. 4 goes. The chance of success, with success meaning you're outside the range, as 1 minus whatever probability we got before, which was in C part 1, and that probability was 0.8985. But if you continue on, you'll get it's actually 1 minus, isn't it? 1 minus 0.898514, like that, because the probability of fitting into the range was 0.8985. Probability of being outside the range would be 1 minus that. Great, so that's our distribution, and you could go ahead and just go probability of x bigger or equal to 1, right? You know how to do that in your calculator, I hope, and you're going to get 0.3482. So the chance of having at least one ball outside the range from a can of balls is actually about 35%. Maybe it's not such great quality. Maybe not such great quality. Notice that that's not the only way to do this question. You can say alternatively that the probability is just 1 minus the probability of all the balls in range. Yeah? And so if you were to go ahead with that, you can do 1 minus 0.898514 to the power of 4, and you'll come out with the same thing. I like the second approach better, to be completely honest. But either one will give you the right answer, so don't be fussed. Don't be fussed in the exam about this. Part D. Part D. So now they want to change the manufacturing process to make their balls better. Always a good idea to stay in business. And you want to change the standard deviation so that 99% of the balls fit within that range. Great. How do you start? How do you start? Well, you could think about what is a equation that has standard deviation in it, because obviously you need to solve for it. And the first one that comes to mind would be this one. Z is x minus mu over sigma, where sigma is the standard deviation. That's a really good start. And so basically that's relating our distribution to the standard normal. Now, okay, where do you start? You want a standard normal value z, where you want basically probability that z bigger than z is what? 0.005. Where do I get that from? Half of 1%, right? Because we want this picture going on. This is what we want. You've got your normal distribution, like so. You've got your mean at 67, and this is what's that upper bound that they wanted? 68.4, 65.6, 68.4, 65.6, and they want this middle area to be 99%, meaning that this little area here 0.005 and that little area there 0.005. There, add up to 1. Great. So probability that our normal distribution, or our z, is going to come in higher than some value is going to be 0.005. Now, how do you define that? How do you do that? You're going to get this. You can use your inverse normal, right? Inverse normal, and you'll find that z actually is equal to 2.5758. There. So your calculator will have an inverse normal function, and essentially what that's saying is that on a standard normal distribution, meaning mean of 0 and standard deviation of 1, the chance of having a value higher than 2.5758 is exactly half of 1%, which is what we want. Great. Plug this back into our formula. Whoops. No, I know z now. I'm not going to do that. What I'm going to do is say, great, 2.5758 equals, now our x, what's our x? 68.4, right? So that's our upper limit from here. Minus the mean, we know that it's 67, over the standard deviation. Oh, look, suddenly we've got an equation to solve. And when you solve this, you will see that standard deviation is going to be what, 1.4 over 2.5758, which equals 0.54. 0.54 what? Millimeters. Remember your units. 0.54 millimeters. There you go. So that's what the new standard deviation has to be for 99% of the balls to fit into that range. Not too bad, right? Not too bad. Getting into part E. So now they're making money, and they say they want to sell balls, selling them once a year. And I hope you're able to recognize that this is a Markov chain. There's a Markov chain happening here, where if the tennis club buys its balls from BBC 1 year, the next year it's going to buy it, or there's an 80% chance of it buying next year, and if it doesn't buy, there's a 15% chance of it buying. The first thing you might want to do is write down that transition matrix. Not yet, not yet. Read the question, and maybe you won't need to. So anyway, it goes, what's the exact probability, part E, what's the exact probability that it will buy its tennis balls from BBC for the next 3 years? Oh, that's not very hard, is it? What's the probability of it happening next year? 3 years. Well, you know that next year is going to be 0.8 because it bought this year, right? What about the year after that? Well, it bought the year before, so it's going to be 0.8, and same with the third year. 0.8 by 0.8 by 0.8, all through you're going to get 64 over 125. Easy question. F. Part F says, what is the exact probability that it will buy its tennis balls from BBC for exactly 2 of the next 3 years? You might be tempted to use that Markov matrix, the transition matrix. But the transition matrix, what does it tell you? Remember what it tells you. It says it can find the probability of you buying the tennis balls at some year in the future, right? It can predict a state in the future. But we're not talking about states here. We're talking about, well, what's the chance of us buying 2 out of the next 3? We're not asking for a particular year. So again, that transitional matrix doesn't apply. Okay, so what can we do? 2 of the next 3 years. Okay, why don't you list out what could happen? 2 of the next 3 years means we could buy, not buy, or we could buy, not buy and buy, or we could not buy and then buy, right? 3 chances, 3 possibilities. 3 possibilities. And maybe what we can do is walk through the possibility of each one and add them together. Yeah? Let's do that. So the probability, okay. So buy next year, so we're just starting at the first one. Buy next year is 0.8, right? We've established that. Buy the year after, again, 0.8. What about if you buy this year but don't buy the year after? Well, it's 1 minus 0.8, right? It's 0.2. So the chance of buying next year, buying the year after, and then not buying is 0.8 by 0.8 by 0.2. Go through a similar process. So the second one says buy, not buy, buy. So the first buy, you know, is 0.8. Not buy after the year of buying is 0.2, right? Now, what's the chance of you buying when the previous year you haven't bought? Look at the question. Come back. You say that if a tennis club doesn't buy its balls from BBC 1 year, there's a 15% chance it will buy its balls from BBC next year. Oh, there you go. That answers your question. 15%, 0.15. So that's the second possibility. Now the last one. So, not buy in year 1. Remember that year 0, so our year? It bought already. So you get 0.2, right? Buying, after a year of not buying, you get 0.15. And then, well, look, buying again. After a year of buying, that's just 0.8. So be very clever. Add all of this up. You'll get 22 over 125. There. A little bit of thinking and a little bit of going back into the fundamentals of how this all happens. Don't just rely on your formulas. And in the blink of an eye, we've come to part G, the last part of the question. And it goes, let P be the probability that the Melbourne Tennis Club will buy its tennis balls from BBC N years after 2009, given that it buys them from BBC in 2009. Find the smallest value of N such that the probability, remember P is the probability that Melbourne Tennis Club is going to buy its tennis balls from BBC, is smaller than 0.45. What's going on? Do you need that matrix? Yes. Now is the time. Now is the time. Right? So let's draw that matrix. Draw that matrix out. We know that, okay, the probability of us buying balls from BBC 1 year is 80% if it bought it the previous year. So 80% goes up here and 20% goes here. Okay. And then we see in the question there's a 15% chance it will buy its balls from BBC next year if it doesn't buy this year. So we know that 15, 0.15 goes here, and so 0.85 is here. That's our matrix. That's our transition matrix. Great. Okay. Now, what do you need to see? What do you need to see? You want to know what happens well, you basically want to find out when does the probability drop below 0.45, right? So maybe a smart thing to do would be to write out the probability of buying in year n, right? So probability buy in year n is going to be simply 0.8, 0.15, 0.2, 0.85 to the power of n, and then 1, 0, right? 1, 0, because that's the result you want. You want to buy. You want to buy. Great. Really good. Okay. Now what? You want this to be smaller than 0.45. Now, first off, I'm going to tell you that there are ways to solve it numerically. Definitely ways to solve it numerically. As far as I know, there's no real way to do it on the calculator. Well, I haven't found a way, at least. I haven't played with it that much. But it is not that difficult to just solve it via trial and error. I mean, it's not too hard for a couple of reasons. One is, you know that as n increases, p decreases, right? So you know that the longer it goes on, the probability will decrease until it reaches a steady state probability, correct? Decreases until steady state. So you know that this thing's heading in one direction, and so all you need to do is try some values out. Just test them out, right? You'll find that at n equals, maybe just test out an intermediate value, 5. At 5, the probability will be too high. Maybe 10. You'll see that 10 is too low. A little bit of trial and error says that for probability, for p smaller than 0.5, we need n equals 8. There. I want to reiterate that trial and error is not an invalid technique. It's a smart technique when you know that every try gets you closer to the answer in a constructive kind of way. And it works out here because as you increase n, p decreases. So when you guess one, you know where to guess next, and very soon you'll have the answer. And so in this case, trial and error is a perfectly acceptable approach. Awesome. Question 3 out of the way. Join us in the next video for question 4. See ya.